So there is a part of geometry that is really, really playful. It is called construction. But when we say construction, in mathematics, construction is something very specific. It's not something that you just put together or make out of construction paper. It's drawing, but under very restricted rules. And what are those restricted rules? Well, these are the two tools that you can use. This is called a compass. And what you can do is you can find a point and you can put the needle and you can draw a circle around this point. And you can change or fix how much this is open. So basically, you can fix the distance and draw circles around the point. And this is called a straight edge. Actually, this is just a ruler upside down, but you're not allowed to use any marking. So you cannot use this to measure distance. All you can do with this one is to connect 2 points with a straight line. This seems very restricted. We can do circles and lines, and that's it. And it's a whole branch within geometry. And actually, it's kind of, let me give you an example. If we call this distance 1, then what kind of numbers can we draw? Clearly, well, if you can construct a square, we're going to be able to construct something like square root of 2. But I'm pretty sure that third root of 2 is not constructible. So that's a subject within algebra of the set of all constructible numbers. But mostly it's geometry, and construction problems are kind of fun. They're in a way analogous to the kind of geometry where you're given 2 numbers of a right triangle, you have to find a third side. It's just the things that you're given are going to be in drawing. So for example, if you're given 2 sides of a triangle, or let's say 3 sides of a triangle, they would be given as line segments like this. And you would have to draw the triangle that has these 3 sides. So in a way, we are pursuing similar things as before, but the answers are just purely visual. There are no numbers involved. Let me show you the first classic construction problem. So let's start with, given a line segment, construct a perpendicular bisector. So one of the first construction problem is you're given a line segment. And again, you're not given coordinates. You're not going to give a number for the length. You're actually going to be given the drawing of a line segment. And it's interesting because if you have to describe the perpendicular bisector of a line segment, you would say, well, it goes through the midpoint and it's perpendicular to the line. But that is not the defining property. Mathematicians decided to define it in terms of geometric location. It's a set of all points in the plane that are equidistant to A and B. See, any point we pick here is going to create an isosceles triangle because every point on this line, including the midpoint, is equally far from A and from B. And that's going to be key in the construction. In construction, the result is hard to read because what we're interested in the procedure. So we usually write down the steps. So the perpendicular bisector is the set of all points equidistant to A and B. We're going to open the compass more than half of A and B. And then we're going to keep this opening fixed. Sometimes you can actually screw that in place. I don't think I will be able to. And we're going to draw a circle with the same radius centered at A and centered at B. Now consider the intersection points of these 2 circles. They have to be on the perpendicular bisector. Why? Because, well, this circle is the set of all points, r distance, let's say this distance is r distance from A. And this other circle is the set of all points at the same distance from B. So this point will have the property that the distance from A and from B is the same, because we didn't change the radius going from one circle to the other. So when we connect the 2 points, Oh, there is another one here, right? And 2 points uniquely determine straight line. And so we just connect these 2 points. And that is the perpendicular bisect. So a few comments. Number one, we write down the steps. It's kind of annoying, but this, once the picture is done, it's hard to read what happened when, the order of events. So number one, open compass to a distance more than half of AB. Why is that necessary? If the circles are too small, they're not going to meet, right? So if the radius is exactly half, they're just going to barely touch, but 1 point is not enough to find a line. So it has to be bigger than half. But then, besides that, anything goes. If I make this circle bigger, it will work just as fine. It's kind of cool. Because you see, the intersection points must fall into the line that we already drew. And it also shows that this is not perfect. That's why we need, I have the shaky hands, but also if you zoom in, these are thick lines. So these are just the ideas of these perfect things that don't really exist, like a line without thickness. And that's another reason why we need to write down the steps. Step two, draw a circle with that radius twice, once with center A and once with center B. And then connect the intersection points of the two circles. This is one of the first construction problems. But also, if someone says, well, here is the straight line, construct a perpendicular line. Well, in that infinite line, you can just pick 2 points and then construct the perpendicular bisector of that line segment. And then forget about those points. That's just, so this is something more than what we might have. Sometimes we might just want a perpendicular line, or sometimes we just want the midpoint. But how do we construct the midpoint of a line segment? I think that's the way. The midpoint is, I don't really see any other way to construct the midpoint than constructing the perpendicular bisector and intersect it with the original line. So this already gives us quite a few tools. One more note, you're gonna see videos. There is very good animations on construction online, and you're not gonna see what I just showed you. You're gonna see something else. Here is the thing. Sometimes constructions involve lots of steps. This was just something very basic, and look how kind of busy it got, right? So what we usually do is, suppose we're constructing the perpendicular bisector. We open up the compass and we basically don't draw the entire circle, just the part that we know we're going to use. So basically, instead of the whole circle, which you're allowed, but it would crowd a more complex problem with many steps. See, I just did those parts where I kind of guesstimate the intersection points would come. But they look kind of silly on their own. They are just parts of those circles that we don't even bother to draw. So this is more like the kind of things that you will see. But the concept is the same, that you're drawing parts of circles that are sets of points equidistant to a point. Let me show you the second easiest construction problem, and that has interesting consequences. Suppose we're given three line segments, and we have to draw the triangle with lines that long. And instead of giving 3 numbers, which in trigonometry, you're going to be able to compute the angles, here we're just given 3 lengths, like so. Actually, this involves quite a few other things, but so construct the triangle with sides this long. Now, the triangles, if measured, must pass the triangle inequality. I try to do it so that it will pass them. So it's also a good idea to sort of draw the final product. For me, I need it for orientation, like what point is what, who is who. Otherwise, I cannot do these problems. So let's say this is this. I don't even know. This is this, and then this is the longest side. I'm just going to call it A, B, and C. and then little a, little b, little c. And then we can say that, well, this looks like the longest, suppose it's the biggest side. So the longest side is A, the middle side is C, and the shortest one is B. Okay. So it doesn't have to be, but I usually start with the longest side. We actually first we just start with a straight line. Okay. And then we randomly pick a point. Yeah, let's agree that I'm not gonna write down the steps. You can rewind and watch it again. So we started with an infinite line, we picked a point, and we said, okay, let this point be our B. And then on this line, we're looking for point C. The distance is 8, that's why I need this picture. The distance is lowercase a, that's the longest side. I kind of knew that because I always start with the longest side. So I put the needle into one end of the line segment given and open up the compass so that it's the other end is where the other end of the line segment is. And once I have that, this is how you copy a line segment. This is how you copy a distance. So now we have, this is little a, and this is C. So, hey, we have 2 out of the 3 points, right? We have B and C. All we have to find is point A. So what do we know about this point A that's missing? We know that the distance from point C is lowercase b, and we know that the distance of A from point B is lowercase c. So here is what we're going to do. Now maybe I should write this down. Just this one step. We're going to draw a circle centered at C with radius lowercase b. You realize that that circle must contain A because A is such a point. So we're going to measure B, lowercase b. We're going to measure up the distance and once we're done measuring it, we're just going to draw a circle around C. Again, often you will see just parts of this circle. Now, we don't know where, but point A is somewhere on this circle. And then similarly, we know that the distance between A and B is this lowercase c. So we're going to draw another circle centered at B with radius lowercase c. So we're going to go to the line segment given. We're going to get the distance on our compass. And then we're going to go to point B and we're going to draw a circle. And now this intersection point is such a point, right? It has the right distance from C and the right distance from B. And there it is. See, I don't know if it's visible. It's not bad. This side is that, this side is that. Okay. Now there is another intersection point. Let me do that one with a different color. Granted, we have 2 triangles, but they're congruent. So construction tells us that if the triangle exists, it's unique. So it is construction that tells us that 3 sides of a triangle uniquely determines the triangle. There's no 2, given 3 line segments, there's no 2 different triangles with those lengths as sides. I don't think that's so easy to get it algebraically. And also, let's just think about what would it look like if the triangle inequality failed? If the triangle inequality failed, these 2 circles would not meet. They would be too small to meet. So that's the other construction problem. Thank you for watching.